Good morning, everyone.
Good morning, sir.
Yes, sir.
How are all of you doing?
Fine, sir.
Great. So, where do we start? What was it that we were doing in the last class? Who can tell me this? What was it that we were doing in the last class?
Sir, first we see the right cycle, then we study the memory sheet.
Memory sheet. What was that called, Abhishek?
Yes, sir.
Data sheet.
Data sheet.
Data sheet. So what were the various components? What were the various contents of a data sheet? Top level pe, quickly.
So size, rows and columns.
Muxes.
Mux input.
Words per
APA.
row and
It gives an
Okay.
information of
So
people.
the first thing that was about the details of the cell, like how many words, how many bits. Then there was this concept of mux. We talked about mux in much more in a lot of detail. Is mux concept clear to you?
Yes, sir.
Any questions related to the multiplexer concept? So if I say that there are 1K words and I want to use mux 8, how many rows would be there? How would be the memory array organized? How many rows would be there in the memory array?
1K by 8, sir.
1K by 8, which is 128.
128.
Okay. Now let me say that there were 24 bits, and I'm using mux 4. So how many columns will be there?
96.
96. So to get the number of columns, we are multiplying mux with the number of bits, and to get the number of rows, we are dividing words by mux.
Yes, sir.
Okay. Now let me say that the intrinsic aspect ratio of the memory cell was 1:2. That is, it was, if the height was x, the width was 2x. If the height was x, width was 2x. To get a square memory instance, how many, like, what should be the ratio between rows and columns?
2:1.
So 2 times, what is 2? Rows or columns?
Sir, 2 times is the width of each row, sir.
Each cell is twice as wide as it is tall. I want a square memory instance, square memory array. So if the number of rows is r, what should be the number of columns?
Twice.
Sir, what is the initial ratio that you mentioned, sir? The ratio of height is to width.
Width of
Is
the memory cell, physical height into width of the memory cell.
what is that ratio value, sir?
1:2. Height is h, so width is 2h.
Okay.
So what should be the ratio between rows and columns now to get a square array?
Ratio, the rows should be twice the columns.
Is this clear to everyone? The rows should be twice the number of columns so that we have a physically square array. Some response.
So the 1:2 was of the cell.
Yes, of the memory cell.
Okay, sir.
Clear? Not yet. अगर नहीं है तो पूछो, because this is an important concept. Okay. So then we went back to the data sheet, and what all did we see in the data sheet? It has the cell structure, then it had the symbol and the pins, the description of the pins. What does active low mean? What does active low mean?
The functionality occurs at when the particular line goes low.
Basically, that's a control signal, and it functions. It prefers its functionality when the signal is low.
For example, we said that chip select, the pin was called CSN. So N was actually put to indicate that it is an active low signal. So different companies would have different ways of telling that this is an active low signal. which meant that memory would be active and this pin is held low. That the functionality that you want to achieve will be achieved when you hold this pin low. For example, for write it was WEN. So write enable N negative. So when the pin is low, then you will be in the write cycle. Clear?
Yes, sir.
Okay. Then we looked at different timing labels. The access time, TAA, cycle time, T cycle, setup times, address setup, hold set, address hold, data setup, data hold, all those things we saw. There were also some numbers that we saw on that particular data sheet. And there were additional pins like scan pins, sleep pin, standby pin, and so on. So there were these additional pins which would take the memory into different modes of operation: idle mode, standby mode, sleep mode, all those, test mode. Remember all that?
Yes, sir.
Okay. Neeraj, you have a question?
Yeah. Yes, sir. As far as I see the memory and other things, the chip select type signals are always kept active low. Sir, is there any specific reason or just like procedure?
This is just convention of ST, let us say. If you go to the similar memory instances of say ARM or with Synopsys, they might not have it active low.
Okay, sir.
This is just convention. They must have some reason of keeping it active low.
Okay, sir. Thank you.
But you should know what active low means. That is why I'm stressing that point. Okay. Okay. Then after these timing diagrams and timing labels, and then there were timing diagrams which indicated where these timing labels were valid or what was the real definition of timing labels in terms of signals. And then we looked at power labels. So what kind of powers were posted there on the data sheet?
Sir, leakage power.
Leakage power was there. Yes. What else?
So first of all, peak current was given.
First of all, peak current was given. Why is peak current important? How
Sir,
many of you are doing VDS? You can put a +1 in the chat window if you're doing VDS. Okay. So in when you will design, when you design a chip finally, you will also have to provide power to all the IPs, all the components on your chip. At that point of time, you need to budget what can be the peak power that any part would require so that you can have that many wires there. See, in your house, when you use fuses or when you put in plug points at different places, what do? You check that, okay, this particular fuse can provide this kind of current. So in this particular room, if I'm adding more power points, then I need to use a different fuse wire. You know this? In exactly the same manner, if there is a peak current requirement of a particular IP that requires a thicker wire to be used or more denser power connections to be made, that needs to be done and the user needs to know about it. That is why peak current is important. What about the other power numbers? What were the other power numbers that were given?
The power dissipation when sleep is 0 and sleep is 1 is also given.
Yeah, power. So that was static power.
Yes.
What active power? So what other powers were given?
Sir, write activity power cycle.
There was power given for read and write cycles,
50%.
separately given for read and write cycles, and that power was given with activity rate. If every cycle is a write cycle, if all the data bits are toggling, then what is the power consumed? And if 50% of the data bits are toggling, then what is the power consumed? Similarly, for the read cycle, if all the output pins are toggling, what is the power consumed? If some of the output pins are toggling, what is the power consumed? So 50% and 100% activity rate power values were also given. So in a sense, the data sheet gave the PPA and lots of additional information so that a user can decide that I want to use this memory and can then use the memory effectively. Are you with me?
Sir, also there was something related to bypass mode also.
Yeah, we also good. Thank you, Raghav. So this was bypass is also a test feature. We will talk about it later in the class. So bypass is a test feature, which was for which there was this pin T bypass. Test mode, test bypass. It could be called test mode by someone else. It could be called synchronous write by some other companies. But yeah, it's a test feature. You will see that in this, whatever it is, whatever could be the pin name, the description should tell you that, okay, this is the pin name, this is the pin that corresponds to T bypass and ST, this is the pin that corresponds to test mode and in ARM and blah, blah, blah. So you should be able to read the description and find out what is the functionality of the pin.
And so by 100%, 50%, we are only meaning like alpha equals to 1 and 0.5, that kind of meaning, right?
Yeah, it is linked to activity factor, but it is not the activity of the memory per se. It is activity on the input pins, like how many address pins toggled, how many outputs are toggling, how many data inputs changed. Because that changes the power consumption. That would now more togglings means more power.
Okay, so I'm looking at the pin toggling. So basically the activity at the pin level.
Yes.
Okay. Okay.
Because it is active memory write, तो मतलब memory तो selected है.
Yes, sir.
है ना? So memory is in a write cycle. Now memory की activity और क्या कहोगे आप? There would be inactive memory write where memory is not selected but pins are toggling. That is purely pin toggling power. Memory active write is pin toggling plus memory activity. So by subtracting these two, you can get an estimate of what is the intrinsic memory power consumption.
सर अगर ऐसे में तो हम वो पिन का पता चलेगा ना हमें.
Sorry.
So when we are saying that pin is toggling and also the memory is active, and only when pin is toggling, memory is inactive. So इनको subtract करेंगे तो पिन का पता चल जाएगा हमें कि what
No.
exactly.
No. Subtract करेंगे तो पिन की टॉगलिंग पावर दोनों में थी, दोनों में subtract हो जाएगी.
Memory का intrinsic.
Yeah, memory intrinsic power you will.
When we don't want it to operate, but it's still consuming some. Okay, got it, sir.
No. Not when we don't. It is about the power consumed by, let us say, row decoders and other circuits which are activated when the memory is active.
Okay. Right, sir. Right. Okay.
Okay. So, any questions from the last class? Yes,
hello, sir.
Rohit.
Sir, in the data sheet, in primary parameter table, there is called safety features. Means what kind of safety features memory can have?
Yeah. So you remember we talked about automotive applications. That in automotive applications we do not want any failures. In life critical applications we do not want any failures.
Yes, sir.
So there are standards. There are standards called ISO 26262 standards. A lot of our teammates have been working on these standards and making circuits compliant to these standards. What these standards entail is that if there is some reason because of which memory could fail, before the failure happens or as the failure happens, I should inform the chip, I should inform the system level that there is a failure, so that we do not latch the failed data, so that we do not put the IF of the commuter at risk.
Yes, sir.
So to be able to do this, we need to add some additional circuits in the memory. That is called safety circuits, or that capability to be able to diagnose and intimate is safety features. So in this particular technology, the technology that ST shared this data sheet with us for, this is the automotive version of their 55 nanometer technology. Since it is the automotive version, there was this option that do you want the safety features in this memory instance or not? Because if you put safety features, there will be more area, more power. There could be some speed penalty also. So the user has a choice. Not everywhere does a user need to put safety features, but in some places they may need to put. So that's the choice.
Okay, thank you, sir.
Faisal?
Yes, sir. My question is about the previous example that we have discussed in the last class, like about the row decoder.
Mhm.
Like initially we had 512 words, so we would need 9-bit decoder. And after the 8:1 mux thing, it got reduced into 64 words.
No,
Now,
64
uh,
rows.
yeah, sorry, sir. Yeah, 64 rows. But you told us that it will still be a 9-bit decoder to select the. I'm not able to go there actually.
Yeah. So how many bits would you need to select a particular row? There are 64 rows
bits.
now.
6
bits.
bits.
How
Yes, sir.
many? So every row has how many words?
Every row has how many? Every row. Uh, f-
Sir,
4
8.
words. 8 words. Sorry.
8 words.
Yeah.
Every row has 8 words. So
Yes,
you will
sir.
need
Yes, sir.
some bits to select one word out of those 8 also. How many bits
Yes.
would you need?
Okay, so three bits for those
Yeah.
8
So
words.
3 plus 6 is 9.
So the row decoder will be as it is.
Row decoder, how
Correct.
can it be as it is? It has 6 bits. Earlier row decoder had 9 bits
Okay,
decoding
so
there.
row decoder has changed, but overall the decoding, like the decoding mechanism is similar. Like it needs 9 bits.
Yeah, if there are 512 words, you will need 9
Yeah.
bits to decode it, na?
Okay,
What's
okay,
the
yes, sir.
challenge there?
Yes, sir, yes, sir. Okay.
The processor sent you something. He said, get me
Yes.
this word. He gave you 9-bit address. You cannot ignore 3 bits.
Yes, sir, yes. Okay, understood.
Okay, na? Yeah. Anything else?
So I had a doubt in there were primary parameters. So there were two terms actually. One was the debug mode, and one was BIST mux, I think so. So sir, I got confused. I mean, I think that I think that their similar functionality or the is kind of similar. I mean, BIST is also kind of doing we are trying to debug the errors only.
Hmm?
So I mean, built-in self-test. So
Built-in is simply testing. It is not debugging. It is simply telling you whether it is working or not.
okay.
What does debug mean? When you do a simulation, you simulate something. Something
Yes,
is
sir.
not working.
Yes, sir.
What do you do?
So we try to resolve it.
How do you
So
resolve
we
it?
add some delay.
What if the failure was because of something running slower already? If you further slow it down, it will only fail.
Okay, yes, sir, yes, sir.
So what do you do?
So I mean, the issue could be because of the wrong functionality also, if I'm observing.
Could be anything. Yeah, you do not
Yes,
know.
sir.
So what do you do?
We debug
You
the
open,
issue.
you rerun the simulation by saying, okay, probe all the nodes. And then one by one, you load the nodes on your waveform and say, is the output of this particular inverter, this particular gate as expected or not? You basically go into details and try to debug where did the failure happen. That is how you would do, na?
Okay. So sir, like when I'm trying to localize the issue, that's what we'll be calling as debug. I mean, where exactly?
I'm asking you, what do you call as debug in your simulations?
So I mean,
What we call as debug in memory, we will come to that later. But what do you call as debug in your simulations? That is my first question to you.
so like when I'm coding, if I want to debug, I mean, I will try to say exactly what exactly is causing the problem, where exactly
Which step failed? If
which
you're
step
coding,
failed,
you will
yes.
go row by row.
Yes, sir.
This row, okay, this executed fine. This executed. Oh, this one. Oh, I was expecting this output. Here is the loop that is failing.
Yes, sir.
That is what is debug.
Yes, sir.
Is it the same as testing your code?
No.
So why did you say testing and debug are same?
Testing is yes.
How do you test your code?
So once I test it, then I will go to debug.
Yes.
Yes, sir.
But
Yeah.
testing is very different from debug, is it not?
Yes, sir.
So what confused you? You already know this.
Yes, sir. So actually, I was not. Maybe I got confused because how they are. What is meaning in this memory context? Maybe that's why the BIS
Yeah.
context and. maybe.
But by default, we can use English language.
Yes, sir. Yes, sir. Definitely. Yes.
So the debug mode is essentially us having some additional insights into what is happening inside the memory. We could delay some parts, we could speed up some parts, we could do something else, we could do something else to localize why is this memory failing. This again would mean that there is additional area, there are additional circuits that are added, so there is additional area. This may or may not lead to any additional delays though, because debug mode should not really lead to extra delays. So when you are very early in the technology generation, suppose you want to design a chip in 3 nanometer technology now. No, 3 nanometer is not even production. So what would you do? You would say, okay, I do not know if everything will work. I need to send a test chip first. In the test chip, let me invoke the debug mode. So that if there is a failure, I should be able to localize what failed. And if I need to improve the process, I will improve the technology process there.
So this part, debug part, will be the part of the post-silicon validation kind of part.
Will be done then, yes.
Okay.
Test is also done then only, no? That is not changed.
Yes, yes.
That has not changed. Debug is beyond test. When test tells you there is a failure and you want to find out more, that is when debug comes into picture.
Okay. Okay, sir.
Clear?
Okay. Yes, sir.
Anything else? So again, these names would be different for different companies, but you will realize that these are the kind of features that almost every company would offer in one way or another. There could be some more nuanced features also that someone may offer. When you look at the data sheet, you realize there is a description there and you should be able to make out what that means. Can we do all that? Because if you go to someone and tell them that you've done a memory course and you're not able to read the data sheet, that would be a pity. So data sheet you can read well. That much can I be assured of?
Yes, sir.
Yes, sir.
Okay, great. So with that, then we move to today's class. Can we?
Yes, sir.
Okay. So today we are going to look at 60 memory cells. But before that, I just want to close one additional point that we had with data sheets. If you remember that particular memory, we called it SPHD, single port high density. In a similar manner, you could have high speed memories also, where the architecture is such that the memory is fast. And you could have low power memories also, where again the overall architecture is designed such that you consume lesser dynamic power. So you could have SPLP, you could have SPHS, you could have similar, nomenclatures. Every company again would have something different, but different kind of optimizations are available. On this slide, I've also listed what are the different levers that memory designers use to to make such memories there. If you want a high density memory, you will use a very dense memory cell, which would have, because it's very dense, the devices are small, so the memory cell current is going to be low. So memory cell current is low means you are slower. And because any additional features means more area, you may not have any additional features there. High speed memory means large memory cell, so that you can have a large current, big drivers, big sense amplifiers, hierarchical architecture, so that you can reduce capacitances that are toggling, and so on. Similarly, for low power, you could have special low power features like retention circuits or floating bit lines, and so on. So again, this is just about closing what we were talking about last time. And with that, I want to come to memory cells. So we discussed there are different kinds of memories, single port, dual port. I'm now introducing you multi-port memories also. And then ROMs also we talked about. So single port memories, the most common single port memory that you would have heard about is a 60 memory. Am I right? Anyone who has not heard about the 60 SRAM? So all of us have heard about 60 SRAM cells. So 60, what does RW stand for? Can anyone tell me?
Read write.
Yes. So this is a single port memory in which you can do both read and write. Now let's come to the two port category. Over there are two cells, both 8E, but one is 2 read write and one is 1 read write. What does this mean?
This means that
One port.
channel of the bit line is just meant for reading, and the other channel of the bit line can allow read as well as write.
Yes. And the second one, both the channels can be used for both read and write operations. Both the channels are symmetrical. What about the 10T cell? 2R and 1 read write. How many ports are we talking about in
Three
this cell?
ports.
Three ports, of which 2 ports are only read ports, and 1 port is both read and write. So if I want to do 3 reads in this multi-port memory, can I do?
Yes,
3
sir.
parallel
Yes.
reads?
Yes.
Yes, I can do.
Yes.
If I want to do 2 writes in this particular multi-port memory, can I do?
No, sir.
No, because only one channel has the write capability there. Okay. Again, this is important so that you understand when you read some technical paper or something, you just should know what this means. So 60, 70, 40, 5T, 12T, 10T, 8T, all this means how many transistors in the memory cell. For a DRAM, we would call 1T, 1C. That is 1 transistor, 1 capacitor. For a MRAM, you may simply call 1T, 1R. RRAM, you may call 1T, 1R, and stuff like that. Or if it's a crossbar memory, there may be no transistor at all. It's just a crossbar there. You will need some transistor, but yeah. Okay. So the number before the alphabet T represents number of transistors in the memory cell. So which memory cell do you think is bigger, 60 or 40?
It should be 60.
60 should be
60. Why?
more number
More
of
number of
devices.
More number of devices, so more area.
More number of devices.
It depends on the size of 4T. Right?
Sir, it depends on the
How are you
write driver size.
How are you sizing the 4T?
Good. Just 40 doesn't mean small cell. It depends on what are the specifications. If the 40 cell is designed such that it has a huge current and 60 cell is designed such that it is a high density cell, 60 cell could be smaller than the 40 cell. We just talked about it in the last slide, nahin? Depending on the optimization, a 60 cell could be denser than a 40 cell or a 5T cell. Also the layout, physically how I am placing those 4 cells, what are those 4 cells? Are they all PMOSes? Are they all NMOSes? Are they PMOSes and NMOSes? That could also change the kind of area we are talking about. Are you able to see this? So when you are simply looking at, how do we put it? We are simply talking about or reading technical papers which talk of 4T cell or 5T cell. Mentally, we might be tuned to think that they have lesser area, that they are denser. What I'm telling you is, don't jump to that conclusion just yet. You need more information to arrive at that answer. Are you with me?
Yes, sir.
Yes,
Okay.
sir.
Now, what does this NOR and NAND ROM mean? Any idea? No idea yet?
Might be it kind of we use a stack which forms NOR and similar kind of architecture.
Yeah. So how is the memory cell organized? Is it organized in a NOR structure or a NAND structure? What this means, we will look at it, I think, in the next class. Then what does this diffusion, contact, metal 1 and via mean for a ROM cell?
Might be, sir, if we programmed in ROM at fabrication level in diffusion itself or contact or metal 1, then it will be called as that.
Very good, Prince. Thank you. So this diffusion, contact, metal 1 via, these are layers on a layout, है ना? Hello?
Yes, sir.
Yes, sir.
Yes, sir.
These are the different layers and the layout on the silicon. So which layer do you use to program this read-only memory? See, read-only memory means what something is already written into the memory, now you can only read it. Something is already written means it is already programmed. So when you want to program the memory, do you use the diffusion layer or the contact layer or metal 1 layer or via 1 layer? That tells what kind of ROM cell it is. So which ROM cell would be most preferable?
So metal one, I think so. Metal or the via one.
Why?
So diffusion. So diffusion. So diffusion is the devices. So if
I do
I'm
not put a device, there is no current flowing. I can have a
Yes.
zero.
so, but I would have more flexibility connecting with the metal one.
Why? I'm manufacturing something. I put a device somewhere. I do not put a device somewhere. Manufacturability तो कोई फर्क नहीं पड़ा.
Sir, could it be the reason for the masks?
Of the mask? No. Anyway, you are making a diffusion. See, या तो ऐसा हो जाता that to write to program the ROM you need an extra mask. We are not talking about that. We're talking about regular. What do you say? Diffusion. You anyway need a mask. You need to make the layers. अब उस mask में एक extra hole है कि नहीं है? How does that change anything?
So, but mask costs are significant, right? So
You anyway are making a mask, na Raghav. You need a diffusion mask anyways.
yes.
If you are programming the memory in metal 1, do you not need the diffusion mask? You will still need the diffusion
Yes.
mask.
Yes.
है ना?
Yes, sir.
There's something else.
डिफ्यूजन तो नहीं होगा सर. डिफ्यूजन तो नहीं होगा.
क्यों नहीं होगा? Diffusion होती है ROM D. There is a ROM called ROM D.
नहीं,
ROM
मतलब
and diffusion.
फेब्रल में सर डिफ्यूजन नहीं होगा क्योंकि ये सर पहला स्टेज अपन डिफ्यूजन में ही मतलब तो करते हैं.
हाँ, तो मैं उसी के समय प्रोग्रामेशन कर सकता हूँ ना.
तो बट
You are saying कि वो preferred नहीं होगा.
यस सर, बिकॉज मैं सोच रहा हूँ कि सर अगर डिफ्यूजन हो जाएगा तो राउटिंग मतलब मेटल का तो हम लोग विया वगैरह कंटेक्ट वगैरह तो चेंज कर देंगे, बट डिफ्यूजन में ही अगर प्रोग्राम कर देते हैं तो फिर इट्स काइंड ऑफ कि तो फिर हटाना पड़ेगा पूरा अपना पेपर जो है.
हाँ, तो वो तो लेआउट बनाते समय कर दूंगा ना मैनेज. लेआउट बनाते समय सब कुछ मैनेज हो जाएगा ना. उसमें क्या है? वो DRC क्लीन तो करूंगा ही.
सर वी नीड अ स्क्वायरिश मेमोरी ना, तो जिसका शेप स्क्वायर होगा उसको.
So whether I use a program something through diffusion or contact, does that change the squarish, the aspect ratio of the memory? We're not talking about mux over here, na?
Okay, sir.
Sir, could it be the reason that if you go for diffusion type ROM cell, it will be mask programmable, whereas when we talk about something like metal-based ROM cell, it can be PROM, programmable ROM. So it can be one time.
No, you're talking about only ROMs. They're mask programmable ROMs only.
Okay.
So how many of you like pizzas? You can put a +1 in the chat window. No one likes pizza? Okay, some people like pizza. Okay. So what do you think? Domino's or something, they are delivering your pizza within 20 minutes. So do they net the dough just before, just when you order, or something is done previously? When you order a pizza, does Domino guy start to mix maida and water and everything as soon as you order the pizza, or something is done beforehand?
The dough
Thing
is
is done.
Thing is done before.
The dough is knead, the dough is leavened. It is even, what do you say, yeast के बाद उसको even वो भी कर देते हैं. Long before they don't even know that you are going to place an order, but they know some orders would come. So because they have done some amount of work already, as soon as you place an order, all that he needs to do is, okay, it's a regular size pizza. I need this amount of dough. I will just flatten it, put the toppings and go ahead. Now that is Domino's. You also get frozen pizzas from the market. You also get frozen pizzas from the market.
Yes,
Or you get a pre-made pizza bases. What do you do with those pre-made pizza bases? If it's a pre-made pizza base, all that you need to do is apply some sauces on it, put the toppings, put it in the oven. You will get something pizza out in 5 minutes. Domino's guys, because he had to do some extra stuff. What extra stuff? He had to actually flatten the dough, then he had to put the sauces. So there was at least one extra step. So he would take a little longer. Similarly, if there is suppose we're talking about a set-top box. Suppose we're talking about a set-top box and we say that there are 4 customers that a particular company, say Broadcom, has to handle. 4 customers could be Airtel, Jio, and Dish TV, and blah, blah, blah. Each one of them needs some different programmation for their boot code because they have different validation codes with their satellites and something like that. So you need to put a ROM in those chips and you need to program it according to the vendor. What would you want? You would want to deliver the chips to the customer as early as possible, or is it fine if you deliver it 4 days, 5 days later, 10 days later? There's a customer ready to pay you money. He needs to go to the market. Would you want to deliver it to him ASAP? That's a figure of merit. That's a thing that he would value, no? Hello?
Yes, sir.
So if I say that the programmation is to be done at diffusion level, then I have to wait for the customer to give me his or her program, and only then I will be able to do the diffusion layer in the first place. Whereas if the programmation is at via1 level, then I know that the memory is exactly the same up till metal 1. So I will already prepare those bases. I will already have the wafers processed up till metal 1. As soon as the user code comes, I will generate the mask for via1 and I will process the wafers from via1 onwards after the customer places a request. What would be faster? Diffusion or via1? What is faster?
via1.
via1. So as higher up metal layer or as higher up layer that you use for programming a ROM, that is what is preferred. Clear? Hello?
Yes,
Sir,
sir.
but still we go to diffusion, right? Is it because it's faster?
Aditya, dobara se bolo, please.
Sir, is it because it is faster you go to diffusion? Like, then everyone will choose to go with the higher layer.
No, if you use the diffusion layer, you could be denser.
Yeah.
Or it could be that in total you have only 3 metals in a given process. Imaging process, for example, we talked about it in the DVD course also. You have only 3 metal layers. You do not want to use 1 metal layer for programming. You would rather go for diffusion. But when you have 10 metal layers on the chip, you can as well use 1 metal layer or a via layer for programming. And great, works well. There could be different reasons why you would use different layers. Raghav?
Sir, is this approach called the gate array based design? I mean, is this the same approach?
No.
No. Okay.
No, we're not talking about gates here. We're talking about memory cells only.
Okay. Okay.
Vaishnav?
Sir, Sir, so read-only memory, sir, we'll be previously putting our standard data into our cell, right, sir?
Standard data. What do you mean by standard data, Vaishnav?
It's already decided. I mean, we can't change that
Yeah,
memory.
read-only memory means whatever is inside the memory, you can't change it. And you can't
Yes,
write
sir.
into the memory now. So you have to know it.
Yes, sir. So, sir, how do we program this data exactly, sir? I mean, you are saying that we'll be programming it on diffusion, contact, metal one, or VR. So, how will we programming that? Because I understood is that we need some transistors to store some kind of data over there. So, I think we can't have any kind of transistor on metal one layer.
Yeah, there could be transistors down there which you could connect or not connect.
On metal one layer, sir. Metal one is used for
Transistors
connection.
are there. If you use metal one programmation, you will either connect those transistors or not connect those transistors. If they are not connected, they are not as good as not there, na?
Yes, sir.
So we will see. We will look into this when we talk about RAM cells. Abhi, I'm just introducing these types to you.
Okay, sir.
We are still in that zone of top level data sheet understanding.
Okay, sir. Thank you.
That if someone tells you that I'm giving you a diffusion ROM, what does it mean? And if someone tells you I'm giving you a VIA1 ROM, what does it mean? When you look at the data sheet, you should be able to understand that. That is what I mean to say. Okay.
Okay, sir.
Now, how to do it, we will look at it later. Okay. So now we come to, so any questions here?
Yes, sir, I have one.
Yes, Mohan.
Talking about the two port, how exactly internally they divide the addresses? Do the two ports have access from starting to ending, or do they divide it?
So we will see. पहले हम single port का एक cell देखेंगे, then we will look at a set of two port cells, and then we will look at ROM cells.
Okay, sir.
Multi-port cells are extension of these two port cells only. Okay. So this is just a primer slide for you guys as to what to expect in today's and the next lecture, or the next to next one. So,
हेलो सर.
Yes, Rohit.
सर क्या हमें हर
I'm not able to hear you, Rohit. Can you please repeat? Rohit, I was not able to hear you. Can you please repeat?
हेलो सर.
Yeah.
सर हम कह रहे थे ना कि सर हमारी मेमोरी जो है हमें हम ऑलवेज क्वेरी से बनाते हैं, ये मतलब हर बार जरूरी होता है क्वेरीज बनाना?
No. At times, the kind of space you have on a chip could be rectangular, and you want a rectangular memory. Mux only allows you to change the aspect ratio as you desire.
Okay.
Okay. Should we move forward? Any questions here? Great. So now we come to what a 60 single port cell is. But before we go to a 60 single port cell, can you tell me what is the simplest, and we discussed this in DVD also, what is the simplest storage element that you know of?
Latch.
Yeah, a latch. And if you want to, store a desired data into it, we call it as an SR latch. Am I right? This is how a SR latch looks like.
Yes, sir.
Now, if I say that I want to clock it also, then I will put a clock. Some extra transistors come into picture, which are clocked. Now I say, see, actually my SR latch hai, it is storing only one data. The Q and Q bar are complementary, expected to be complementary to each other. Hai na? So, what do you say? Why have two input pins, R and S? Why can't we have just one? So what is it called then?
D-Latch.
D-Latch. where you say, okay, there is D and there is D bar, and the output, and you're storing Q there, and Q bar is also available to you. Now, this D-Latch, if I ask you to implement it in CMOS logic, can you do this for me? D-Latch, can you implement it in CMOS logic for me quickly and tell me how many number of transistors you need? You can put the number of transistors in the chat window. D-Latch, I want you to implement, use complex gates. No problem there. Use complex gates, but implement it in full CMOS logic. How many transistors do you need? Raghav is saying 18.
So 12.
Vaishnav is saying 12. Okay.
So 14.
14. Okay. So
18.
Lakshay is saying 18.
Yes.
Sachi, did you also make the inverter, D2 data bar inverter? So some of you are saying 18, some are saying 14, some are also saying 12. So in reality, if you also need to make that inverter there, you would need 14 devices, something like this. So 12 devices for the complex gates and 2 devices for the inverter. This is the CMOS implementation. Can you just quickly check if this meets the, if it is equivalent to the circuit that we saw earlier? We have used complex gates here. So it is 14 transistors. But we wanted a 6 transistor memory cell. This is the simplest clogged memory cell that we, this is the simplest clogged storage element we're talking about, but somehow everyone said SRAMs would have 6 transistor cells. So how do you reach 6 transistors? So what we say is that, look, for a memory, when I'm talking about a big memory there, I need, so there could be 1024 words in a memory, but I want to access only one word at a time. So in 1023 words, the clock will not go. So clock will be 0. Of the 1024 words, one word I access. In the 1023 words, there's going to be no clock. So if clock is going to be 0, then do you realize that this transistors are almost always on? If I assume that the probability of selection of any memory cell is equal, or any word is equal, then the probability of this transistor being off in any given cycle is 1 by 1000, let us say. That's a low probability, is it not? So if I say that I want to save area, anyways, for more than 1000 cycles in 1024, or in fact 1023 cycles out of 1024, this transistor is going to be on. So effectively what is happening? VDD is getting transferred here in almost every cycle. So only except the selected cell, VDD in which whether VDD arrives here or not is dependent on these 2 transistors. Otherwise, in all the other cells, this node already has VDD. Are you able to see this?
Yes, sir.
So what I say is, yeah, this one cell, the selected word, we will look at it differently. But to save area, if I connect VDD there, I save 4 transistors. You see. However, when I remove those 4 PMOSes on the top and put VDD here, what happened? See, over here there were these transistors which carried D and D bar. Now they are no longer there. If these 2 transistors are no longer there, then what happens? I need to say that if D is equal to 1 over here, initially when clock was 1, D was 1, what would have happened? When clock was 1 and D was 1, this node would not have gone to VDD. Because both these transistors would have been off. D was 1, clock was 1. So both these would have been off, but now this is VDD over here. So what happens? It means when I want to write 0 onto Q bar, it will be difficult now. Because there is this PMOS which is connecting VDD here. So now, even though I saved area, my ability to write into latch has degraded, and it has kind of become ratioed sizing. So I have to take care of sizing of this PMOS and the strength of these devices to say whether I am able to write 0 in the memory cell or not. Are you with me?
Yes, sir.
So please repeat the last part.
So what we are saying is that because this PMOS is on, now I want to write a 0 here. It means initially there was 1 here. If it was 1 here, then the 0 was written on this side. Are you able to see this?
Yes,
If 0 was written on this side, it means this PMOS was conducting current.
Yes, sir.
Now you want to write a 0 over here. So what this means, D is equal to 1, CK equal to 1. You want to sync the current.
Yes, sir.
I will be able to sync the sufficient current only when the strength of this PMOS is smaller than the strength of this stack of NMOSs.
Yes, sir. Yes, sir.
So sizing of the devices now plays a role in the functionality of the memory cell.
Yeah, okay. Yes, sir.
To save area, I have to now take care of sizing. But the area gains are humongous. You see, instead of 14T, you reduced 4 transistors from there. Humongous area gains. So you want to maintain that. Now let's look at, now that we are here, let's look at what else can we do to save area. So the first thing we do is we just simply reorganize this cell now. If you look at it, this is an inverter now. These two are inverters. So I can actually reorganize the cell as something like this. Are you able to see this? I simply kind of picked this stack up and rotated it so that it appears like this. I've also put the clock terminal inside and the data terminal outside. It doesn't change the functionality per se. So now I say that, see, memory cells are organized in an array. So let me look at an array view now. So this is what my array view would be, a 2x2 set of storage elements. Now I say that, see, when we looked at the memory array, what did we say? I will have one data pin here. It will be able to write into all the memory cells, and it will write into that particular memory cell where the word line is selected. You remember this?
Yes, sir.
So I am saying that in reality, there is only one data pin per column. So this is D2, then this is also D2. And if this is D1, then this is also D1. What that means is I can pull these inverters out of this memory cell. So my 14T memory cell is now appearing to be 8T memory cell with no loss of functionality as of now, except that I have some sizing constraints built in now. All that I did is I shared the inverters across columns. I can do that. Is it okay?
Yes, sir.
So then what we do is we say, see, there is this D1 over here, there is this D1 over here, D1 bar over here, D1 bar over here, D2 over here, D2 over here. So there is some additional element which has the same vertical behavior. and I do something about it. And I pull this D1 NMOS and D1 bar NMOS and D2 NMOS and D2 bar NMOS outside again into the common area. And bingo, I appear to have a 60 cell now. It is just that instead of calling this as a clock, we call this as a word line. And these vertical signals are called bit lines. And this D1, D2, these NMOSs, these are now available not inside the memory cell, but in the IO region, and we will call them write drivers. Is that okay? Any questions? Clear?
Sir, can you repeat the part where the inverters were shared across the columns?
Okay. So if you look at that slide, what did we say? We said that in reality, because there is only one data pin per column, so I have to access only one word. And I know, because we looked at memory organization earlier, we know that in a memory, we need one data pin per column or per multiple columns actually. If there is a mux, then only one data pin is needed. So in reality, this D2 is not going to be different from D1.
Okay.
So if it is going to be D1 only, then why put two inverters and put an inverter in every row? Put that inverter down there. So we put this inverter down here. Then we looked at this set of NMOSs. We said, oh, these NMOSs have the same signal. So I shared them also, and I came to this stage. Is this clear?
Sir, so when we were removing those clock transistor, when you were saying only one will have a clock out of 1024 transistors, but सर हमको पता थोड़ी है कि इसी पे आएगा तो इसके हटा देते हैं.
नहीं हम तो सबका हटा रहे हैं ना इसलिए. That is why we removed it for everyone.
Okay. Okay.
We didn't remove it only for one cell. We removed it for everyone.
Okay. Okay.
And we said we were bringing in a sizing constraint now.
Yes, sir. Okay.
Sir.
Yes, Raghav.
So you have mentioned the clocks as different clock 1 and clock 2. So sir, जो हमारी internal clock generate होती है, वो हमारे row decoder में जाएगी, and based upon my address bits, वो fill connect होगी in word line से मतलब. So मतलब ये दो.
That is what is decoding, ना? Decoding means address के information के basis पे आप कुछ select करोगे.
So but technically they are not different clocks, right? They're different word lines, but connecting to the same clock, like depending upon the address bit.
Yeah, so you gave clock only to the selected word, na?
Okay, so but they actually there's only one clock. It is only connected to different word lines depending upon that.
Yeah.
Yes. Okay.
Now, because word lines etc. are not clocks, that is why we changed the name from CK1, CK2 to WL1, WL2.
Yes, sir.
These are decoded signals, but they are clocked. Only when the clock comes will you get the word line, is it not?
Yes, sir.
So they can be considered as clocks also. For this particular memory cell, it is like a clock.
Okay.
Okay. Clear? Any further questions?
Sir, BL1 is bit line 1. B1 means?
Bit line bar. So Q and Q bar, bit line and bit line bar.
Sir, So in this IO region, the D1 and D1 dash transistors will be called as right drivers, or this whole structure, this inverter D1 and D1 transistor?
Yeah. So we'll come to that later. Doesn't matter. It's a point. It's what it would be called as whatever.
Okay.
See, have you understood the concept? That is what my question is. Whether we call all these 4 transistors as a right driver, or there are 10 other transistors that also come into picture, we're not even talking about that yet. No, right driver design is a separate thing. You'll look at it later. But yeah, this becomes a part of the right driver.
Okay, sir.
There could be other stuff also there. It's not, memory design is not so simple as I've made it appear to you. Don't worry. Go into more details. I'm going into details slowly so that you don't get overwhelmed by ye kya ho gaya.
Sure, sir.
So with this, now we say that my one memory cell has only 6 transistors, where there is bit line bar, and word line. They are the 3 interfaces. Some things that go out and in. They carry information in and out of the memory cell. They control the memory cell. And then inside the memory cell, you have the Q pin and the Q bar pin. You could also call it Q bar, whatever. Okay. So now how do you read and write into the memory cell? See, until the time it was a D-Latch, you knew you would get a 1 at the Q pin and a 0 at the Q bar. But now Q and Q bar are no longer accessible. Now I just now said that word line, bit line, and bit line bar are the only ports that you have. The user can no longer access Q and Q bar. So how does he read? How does he read?
So through WL and bit line?
Yes. So if we say this is the 6 transistor memory cell, now over here I have changed the nomenclature from Q and Q bar to BLTI and BLFI. Okay, but it means the same thing. Don't worry about that. Okay. So what we do is, before anything happens, we keep, before the word line comes, we actually keep the bit lines pre-charged. Pre-charged means that they are, so these bit lines are essentially capacitances. So we say that these capacitances are held at or pre-charged to some voltage level. Let us say VDD itself. Let us say they are pre-charged at VDD level. When word line goes high, what happens? These NMOSs will turn on. These NMOSs are called access transistors. These NMOSs will turn on. They will allow access to the contents inside the memory. And because there is a 0 written here, the charge would start to flow like this. On this side, over here also it is 1, over here it is VDD. Both sides is VDD. Over here this was VDD and the other side was 0. So some charge will flow like this. And this bit line will discharge. What happens? One bit line discharged, the other bit line did not. And that is what will now in the IO region trigger the sense amplifier to complete the read operation. Is this clear? Are you able to see this? Any questions to the read operation?
Sir, can you explain this?
What part did you not understand, Abhishek?
Sir, bit line bar is discharging that part, and this is bit line bar and pin. Yes, sir.
Okay. So when word line gets selected, do you see that? Okay, this is, so what I said was both the internal nodes are pre-charged to VDD. Both the bit lines are pre-charged to VDD. Yahan tak clear hai?
Sir. Yes, sir.
Okay. Now, when we turn the word line on, what happens? These are NMOSs. They will turn on.
Yes, sir.
Now, what happens? When they turn on, there was a 0 stored on this side. So this NMOS will now start to conduct some current.
Yes, sir.
Will there be any current here? No. Both sides are VDD.
Yes, sir.
So some current will start to flow from here. Now this is a capacitor. You remove some, so when a current flows, some charge is removed from this capacitor.
Yes.
So when a charge is removed from a capacitor, what happens to its voltage?
Decreases.
It reduces.
The voltage falls. So over here, because bit line was connected to BLTI, which had 0 stored on it, my BL voltage falls. After some time, there would be sufficient differential between bit line and bit line bar, and I will be able to trigger the sense amplifier and complete the read operation.
Yes, sir.
Is this clear now?
Yes, sir.
So BLTI will get charged to VTD minus VT, right?
Why? See this, if there was a 0 stored here, if there was 0 stored on this side, then there was 1 stored on the other side, no?
Yes, sir.
So if there is 1 stored on this side, so what happens? This NMOS is also on.
Okay, so okay.
It will sync
Yes,
the
sir.
current.
It will sync the current. Yes, sir. Yes, sir. Okay.
है ना? In fact,
Yes.
if this NMOS is not strong enough, what will happen? You very rightly said, this BLTI will start to rise up.
Yes.
If this BLT starts to rise up, what would happen?
The discharging of from BL will be slower than, like,
Yeah, the discharge from BL will become at a slower rate. But
yes, sir.
still more worrisome thing is, you stored a 1 here, you stored a 0 here. Now this is no longer 0. This is almost 1.
Yes, sir.
So what happens?
Data
My data can get corrupted. My data can get corrupted. So during read cycle or when the word line is on, that is when my stability is lowest, because this BLTI is going up. If there was no flow of current, this BLTI would remain at 0. Are you able to see this? Because even if
Yes.
it had gone a little bit up, the NMOS is on, it will discharge. But when word line is on, then there is a current coming from here also. And therefore my stability is slowest, is the least when the word line is on. That is where we will finally measure the noise margin of the memory cell. Okay. So read operation is clear. Any questions for the read operation?
So I'm able to understand the operation, but actual में read क्या होगा अभी इसमें? Read क्या हुआ? हमको क्या मिला?
The bit line went to 0. So the sense amplifier would say that bit line had stored a bit line, BLTI was storing a 0. So the user may interpret it as read 0.
Okay. BLTI को हम देखते हैं, BLFI को. Okay.
No.
ठीक है.
ऐसा
Okay,
मैंने
sir.
कुछ नहीं कहा.
Okay.
मैंने कहा user may interpret it as. मैंने ये नहीं कहा user will interpret it as.
Okay, sir.
It is your prerogative as a designer as to what it means. You may call it 0, you may call it 1. It depends on what you wrote. If when you had to write a 0, you stored 0 on BLTI, you would read it as 0.
Yes,
If
sir.
when you wanted to write a 0, you stored 1 on BLTI, you would read it as 1.
Yes, sir.
Okay. So read and write are coupled. You cannot look at them independently. So जो आपने लिखा उस basis पे आप उसको interpret करोगे whether it is a 0 or a 1. Is that okay?
Sir.
Yes, Vaishnav.
So, sir, previously we were seeing that our bitline and bitline bar were having an inverter in between, sir. So both, how can they have the same value at the same time exactly? I mean, during start, we were giving
that was
one
that was a simplistic view for you. As I said, we are going to more and more real views. So these are two capacitors. I can charge those two capacitors at VDD now.
Okay, so there is no inverter in reality in between them, but we are just storing the value of this bitline and bitline bar with the help of a capacitor. That's
yeah.
Okay.
So in reality, if you notice, there was never an inverter directly between the bit lines. The inverter was on data pin and that went to the write driver. Bit lines पे कोई inverter नहीं था.
Yes, sir. Yeah. Yes, sir.
Yeah. Ranjit?
Sir, I didn't understand how if the NMOS is slower, then how will the data corruption occur? I didn't understand that.
We will come to that. We'll look at stability in much more detail in a little while. Don't worry. There will be some homework assignment for you also to understand this. So it is not a graded assignment. So you can or may not, you may or may not do it, but there will be something that I will ask you to do. We will come to that. Anything else?
VLTI means?
Doesn't mean anything. It's just a name. BLTI. T could represent true node and I could represent internal. So true and false. I could have called it Q and Q bar. I could have called it anything. Don't worry. नाम है बस.
यहाँ पे जो इन्वर्टर का सर पुल डाउन है उसको सर ज्यादा वीकर रखना पड़ेगा या स्ट्रॉन्गर, बिकॉज हम डिस्चार्ज करना चाह रहे हैं जो BLTI का नोड है.
Good that you are coming to these questions. I want to arrive at these questions in just a little while. We'll jointly find the answers to these questions. What do you think? How would you size this
Sir,
pull down transistor?
I think whatever the thing जो ये लेफ्ट वाला NMOS है वो पास करेगा करंट यहाँ पे, so that current should be that pull down NMOS ज्यादा फास्टली उसको संक करना चाहिए, I think.
Yeah. So what we essentially want is that even if there is a lot of current coming from bit line onto the BLTI node, all that current should be immediately shifted away without significant rise in the level of BLTI. So that there is least impact on stability. So if I have to sink lots of current without significant VDS, the pull down should be strong, much stronger than the pull pass gate there. Much stronger than the access transistor there. So we will see. We will come into this sizing wala business in just a little while. Ranjit? Okay. Neeraj?
Yeah, sir, actually I'm a little bit confused, like what we are reading. So like what I interpreted is that like we are just making on BL or BLB, like on the basis of that we are reading. Is that correct?
So we're creating a differential between bitline and bitline bar, and that is what we will amplify in the sense amplifier.
Yes, so sir, like if the case we take like BLTI is 1 and BLFI is 0, and like then the BLB will will fall down, then we can say that we are reading 1.
Yes.
Okay, sir. Thank you.
Okay.
Sir?
Yes, Vaishnav?
Sir, so I don't know if I can ask this question right now or not, but sir, now my bitline has got discharged, and this difference which creates between the bitline and bitline bar, that is sent to the sense amplifier, right, sir? So, sir, for my sense amplifier to work, the sense amplifier signal should be enabled. So, I mean, there should be some other wire going from between these positions to the sense amplifier to enable that. So, saying that, okay, my so you can work on with my sense amplifier operation when my bitline is down and bitline bar is high.
So we had that SAN horizontal wire in the IO region, na?
Sir,
We
I
showed
mean,
that.
so is that wire coming from somewhere around here?
How can it come from every memory cell?
Oh, yes.
We talked about the reference bit cell and reference bit lines and reference word lines, na?
Yes, sir.
That was exactly for this purpose. So
Okay,
that we
okay.
could generate the enable signal for the sense amplifier.
Got
We'll look
it.
at that in more detail later also. Don't worry.
Yes, sir.
So now, how does the write happen? For the write to happen, see, you already know what you want to write. Now, it is 0 over here and 1 over here. If you want to write into the memory cell, you would actually want it to go to 1 and it to go to 0. So you already know what data you want to write into the memory cell. Based on that, what you do is, even before the word line comes, you keep one bit line at 1 and you discharge the other bit line to 0. Then when the word line arrives, what happens? Over here now, this was at VDD, this was at 0. Over here, VDD 0. So on the left side, regular read operation will start to happen. But on the right side, what happens is this 1 starts to get discharged through the access transistor. Okay? When that discharges, what happens? As it starts to go to 0, this PMOS will turn on. So initially, when this was reading only, this was the voltage. We ensured that VLTI does not rise very much. But after a lot of discharge had happened, what happened? This PMOS turned on. So this will take this node to 1. And we would say that I have flipped the contents of the memory cell. I have written 0 there and 1 here. Okay. Any questions on the write operation?
Yes, so the bit line is discharging.
Bit line has?
Bit line is also discharging.
So we discharge the bit line through that write driver.
Yeah.
The side where we wanted to write a 0, we discharged it through the write driver.
The bit line is in the read set.
So this one we will keep pre-charged. The bit line. So because we know this is a write cycle, what we could do is we could actually have a PMOS connected here, which is on during the write cycle. So this would remain at 1. This would not discharge. That we can do. We may do, we may not do. That as a designer, I have to decide if it helps me or not.
Sir,
how are we deciding where we need to write one, left side or right side?
The user gave you some data. Based on that, you decide whether BLTI needs to be 1 or a 0.
Okay, so suppose, sir, here if you want to write one at the VLTI side, so what I should do?
वही तो हमने कहा ना. If I want to write a 1 on BLTI, I know that BLFI needs to be written to 0. है ना? BLTI is equal to 1 means BLFI needs to be at 0. So that is what we just did. We took BLB to 0 and we wrote 0 on BLFI. When we wrote 0 on BLFI, BLTI automatically went to 1.
Not clear, sir.
Okay. So if you want to write a 1 on BLTI, it essentially means that you want to write a 0 on BLFI. Yes?
Yes, sir.
So that is what we just did. If I want to write a 0 on BLFI, what did I do? I took BLB to 0. I wrote a 0 there. Once I wrote a 0 there, what happened? The PMOS turned on the BLTI side and it wrote a 1 on that side.
Okay, but sir, initially, if the stored data was at VLTI was 0, and VLFI,
that was what the case was, na? If you look at it, what was the case? We said BLTI is 0. हमने यहीं से तो शुरू करा था. We said BLTI is 0. We discharged the bit line bar to 0 now. Therefore, we discharged BLFI to 0. Once BLFI went to 0, we said that BLTI will get charged through the PMOS.
This thing I understood. I am saying that sir, पहले से ही VLFI पे 1 है, but now user send that VLFI पे 1 लिखना है.
Now, if you want to write 1 on BLFI, then you will put bit line to 0 and maintain BLB at 1. Basically, what I am saying is you cannot write a 1 inside a memory cell because you are using NMOS pass gates. Can you transfer a full 1?
No.
You can only write a 0.
Yes, sir.
Are you able to see this?
सर राइट में दो हमारा 1 और 0 साइमल्टेनियसली राइट करना स्टार्ट होगा, बट हमारा 0 पहले राइट हो जाएगा
Yes.
और फिर वो उसको रीइंफोर्स करेगा 1 करने में.
Yes, you will always write a 0 first because you have NMOS pass gates. If you had PMOS pass gates, you would write a 1 first.
Okay.
Okay, Sachi?
Yes, sir, I want to know, like, how is this bitline bar is getting discharged? I mean, is it by using that D bar data is 1 so that it
Yes,
is
the
starting from-
drivers, yes.
Okay. And so, sir, if D is 0 and D bar is 1, so what means by that data, we say that we want to write 1 or 0 here at PLT. Okay.
Yes.
Okay,
So that
sir.
we decide as designers.
Okay, sir. Okay, thank you.
Neeraj?
Yeah, sir, as much I understand, like if we have to write 0, so sir, can we say like we keep BL at 0, BLB at 1, and then we raise up the right line?
Yes, if you want to write the other data, like we just wrote 1 0 in the memory cell. Now you want to write 0 1. So now in the
Yes,
next
sir.
cycle, you will take bit line to 0. You will maintain bit line bar at 1, and you will write 0 on the BLTI side.
Yeah, yes, sir, yes.
Okay. Ranjit?
Sir, I too had the same doubt as what Raghav said. So we start the right cycle from the discharging node, and once this node discharges, it drives the other inverter, which which charges the other node.
Yes.
Okay. Yeah, understood, sir.
Sir, you said either of bitline or bitline bar one should be chosen. So how are we deciding which one should be chosen?
See, suppose the user wants to write a data 1. I, as a designer, can decide that when the user wants to write data 1, whether BL will go to 0 or BLB would go to 0. I can decide that. Okay? And then all that I need to do is that during read, I should know, okay, during write, I said for 1, BL had to go to 0. So when BL goes to 0, I'm reading a 1. So during read, you will use that information that you used, that decision that you had made during write, you will use during interpreting what is read.
Okay, means for read वाला हम information के according decide करेंगे.
Read का interpretation write के basis पे decide करते हैं. Because you write and then you read.
Yes, sir.
Sachi, you have a question?
No, sir.
Okay. So anything else? Any other question on the write operation? Is the write operation clear? Okay. So we are almost at the end of the class. What I will do is I will just introduce. So what we did see over here was that there is in a 60 memory cell, there is some ratioed thing that is coming into picture. There is this PMOS that is sinking some current. There is this NMOS that is sinking some current, that is driving some current, and so on. So there is a ratio thing that will come because we removed those 4 PMOSs in the first step. So because of which there are certain figures of merit linked to a memory cell. The first and the foremost, the most important figure of merit of a memory cell is?
Area.
Area, sir.
It is so important a figure of merit that I tell you that you call a memory cell. You know, if I want a memory cell to be included in my library, I would call it by the area. Area defines the name of the memory cell. I would say 149 LL. So 0.149 micron square cell in the LL flavor, or 121 HS. So 0.121 micron square cell in the HS flavor. So area is such an important figure of merit that a memory cell is recognized by area. Name ही वो हो जाता है उसका. Okay. Beyond area, there are some electrical figures of merit, which are cell current. So we will look into these in more detail in the next class, which is also called as read current. Then there is bit line leakage. Cell stability we looked at very fleetingly today. We will look at it in more detail tomorrow in the next class. Then there is something called retention voltage. I'm just leaving these terms with you so that they kind of stay in your mind, and you can, if you want to, just read about them somewhere. Okay, I'm not saying whatever you read from the internet would be right or not, but if you want, you can read. We will discuss them in much more detail in the next class. Then there is something called as write margin. So you see, we took the bit line to 0. You remember when we were writing, we took the bit line to 0. In reality, can you really take any node to full 0? It's a capacitance. You will discharge it through some resistance. So in reality, it will follow that RC curve. If the R is very less, it will discharge very fast, but still arriving at 0 may not be possible. So how high above 0 can it be that I will be able to write into the memory cell? That is what is called as write margin. Okay. Write time is intuitive. The name itself suggests how long does it take to write into the memory cell. And we just now saw that write 1 happens slower than write 0. In a 60 memory cell with NMOS pass gates, 0 is written first and then 1 is written. So write time is typically measured when 1 is written completely. And then leakage. Leakage is a very important figure of merit, because as we just saw, that out of 1024 words, even when the memory is accessed, only one word is on, the remaining 1023 words are off. So when they are off, it means they are simply leaking, not doing anything else. So leakage is a very important figure of merit for a memory cell. Okay. So these are the figures of merit that we will look at in the next class. We will go into more detail. We will look at how these figures of merit impact the sizing constraints for the different devices, and subsequently we will look at stability and other features also in more detail. Okay, so we can close the class here. Any questions?
Sir, in the last slide, right cycle wala, first we are reading के जो अंदर की स्लाइड से 10 है या 01 है, then we are deciding कि BLB and BL bar क्या होना चाहिए for writing purpose.
No, we get the information from the user. What is D? What is the data that I need to write into the memory cell?
Okay.
Based on user input, I decide whether I want to discharge bit line or bit line bar.
Okay, if the same data is already there and the user has also given the same data, then there will be no change in the memory content.
Yeah, then the memory contents will remain same.
Okay. So पहले क्या storage is not of our focus
I don't
point.
know. I don't know what was stored earlier. When I'm asked to write, I simply write.
Yes, got it.
Anything else? Okay, then let's meet on Tuesday then. See you.
Sir,
Yes,
sir, actually not later lecture, so some other
so,
out.
Yeah, 2 minutes later. Okay.
Okay.
Sir.